Okay? So require that you can flow along positive time and negative time. Obviously, you cannot reverse time in control theory, but luckily, if you can reverse the flow along the vector field, it's equivalent to reversing time. But the issue is that some of your actuators maybe cannot reverse direction. Okay? We'll talk about that later. So, and obviously V1 up to Vk are in your family. So, any question about this set? So, this set is a set of maps. Each element in that set is just a map that takes points from M to another point in M, flies along these vector fields. Along V1 for some time, then V2 for some time, then V3 for some time, and so on and so on. So, we'll define the orbit O of F through this point x0, which is psi of x0, such that psi is in def F. So this is called the orbit of F through x0 in M. So you start, this is, we're focusing at a point in M. Starting with this point, go and flow along these guys. Flow along V1, V2, V3 for whatever time you like. Here are the final results, okay? So here is something. So here is x0. Say you have two vector fields, V1 and V2. Or the other way around, because we have the reverse, right? These are the points that you reach. Again, at each point, I can flow along V1 and V2 again, and V1 back, and so, right? At any point, you have two branches, and the collection of all these points, they look ugly, but this is the orbit. This is the orbit of F through x0, okay? This book has this very nice picture, which I can get, right? Edit, yes, snapshot, very good. And put it here. It's better than mine, so don't bother with mine. Can we? No, it would be missing. Okay. Let's put it down. Actually, let's have it smaller. So this is the orbit, okay, through Q0 by these two vectors. You can see we can flow forward and backward. Here, this is the reachable set in control theory. They call it sometimes the attainable set from Q0. We're just allowed to move forward only on time force, right? So this is the difference. The issue is that the reachable set is very hard to characterize its nature and its topology. This, guys, is much easier to deal with. So for example, so I'd like to say something here. So this orbit, assume that you can move forward and backward in time. That's okay. This orbit represents what? All the points that you can reach. This is your maximum ability, maximum capability. What else can you do? This is all what I can do. Just move along F1 for some time, then F2 for another time, and so on. So this is all what I can do, right? So this is your ability to reach points. Reachable points, it's actually more than the reachable points, right? Reachable points assuming that we can reverse time, right? Okay. So you have a theorem here that OX0 F is a connected, immersed submanifold of M. So it's a connected set. It's not the union of two disjoint subsets. Okay, it's connected. Immersed submanifold. Submanifolds. So remember, if you have M here and you have any subset open, N subset of M open, N is open set. Obviously, N is a manifold. itself, right? Because it will inherit the manifold structure from this guy. If you have maps to Euclidean space, well, it will map n as well, right? So n is also a submanifold of M. This is not what we're talking about. Immersive submanifold is a submanifold that does not inherit the manifold structure from this guy. It has its own manifold structure. So I will not talk about it more. I'd like to save some time for more important stuff. But this is what we mean by an immersive submanifold. Well, what's the good thing here? The good thing is that, oh, you're telling me that this orbit has the manifold structure, so we can talk about the tangent space, right? I mean, tangent space is not defined for anything. Here we have a manifold, so okay, we can talk about tangent space. The theorem gives you, what's the tangent space? Remember, O is your set of all your reachable points. This is your capability. So this is what?
Set of all possible velocities.
Yeah, this is your maximum ability for the velocities. This is your all attainable or achievable velocities, right? This is your capability. This is what? This is the following set. Psi star V for all psi in depth and V in F. The adjoint, the pullback of V along psi, okay? And psi are those concatenation of flows, psi and depth F. So this is your velocity. So this theorem is very important in the following sense. First, it gives a manifold structure to the orbit. Second, it tells you, it characterizes the attainable velocities. It tells you something about your ability. This is your maximum ability. But the characterization is difficult. How can I compute all these guys? Because psi's are flows along vector fields, right? They are flows. So it's okay, but it's not very useful in practical sense. We know that if we have a vector in F, obviously this vector is tangent to the orbit for all x in the orbit, right? Because its flow is inside. If you have all the times are 0 except for this guy, then this is one trajectory and V is tangent to that trajectory. Okay. So if we have V and W is in F, is V and W at x in the tangent space to the orbit? Are they tangent to the orbit? What do you think? Is this statement correct? Last times we proved that this guy is tangent to the following curve. What's the curve? Flow along, right, this is sometime along V, along W, along negative V, along negative W, right? And this guy is inside the orbit, right? This is concatenation of vectors. So yeah, the Lie bracket is also tangent. And you can keep doing Lie bracket. So the Lie bracket of V with respect to this guy is also tangent. The Lie bracket of W with this guy is also tangent. So we will define here something called the Lie infinity of that set. So keep doing Lie bracket iterations until infinite. Luckily, at some point, luckily for any point x in the space, you don't go to infinity. We're guaranteed that after some finite n, but we don't know what's that n, a priori. But we're guaranteed that at some finite n, we will be able to stop, luckily, okay? So this is a Lie subalgebra, or what we call it, Lie algebra of F. Obviously, it's a subspace of all the vector fields, right? So now I have this characterization. This is my maximum capability, all attainable velocities. and I know that any Lie bracket in here, right? All the Lie brackets are in here. So this means that the Lie infinity f, what's the relation between Lie infinity f and the tangent space if I evaluate it at some point? The tangent space. What's the relation? What do you think? We're saying all the Lie brackets, where? All the Lie brackets are here, right? So this is a subset, but I'm not sure if it's equal or not. Is it equal or not, right? As the Lie, this is all my maximum capability, and I know that the Lie brackets are in there. They're providing me some velocities. Is it all velocities or not? I don't know yet. And I'll give you that example, so we have time. Luckily, I'll give you that example quickly. Consider this differential equation. X dot equals 0, u is a control. Y dot equals h of x. So in our language, we have two vectors, 0 h of x plus 1 0 times u. Okay, so this is say x, and this is y, vector fields. Okay? But I will have a very particular h of x here. This is my h of x. So this is x. Remember, this is in two-dimensional. H is just function of the first argument, x. So here is h of x is this function that we talked about before. It's flat here around 0 and goes like this. So h of x is 0 if x is negative, and e to the negative 1 over x squared if x is positive. So h is smooth, you can differentiate it how many times, but it's not analytic. Okay, so h of 0 is 0, and h prime is 0 is 0, is actually h of any n of 0 is 0 for all n. H is smooth, but not analytic. Okay. Delta as a span of, or f, whatever, span of x and y. So span of 1, 0, this gives you motion along the x-axis, and this guy which gives you motion along the y-axis, you don't always have this kind of capability, because h obviously vanishes for all negative x's. So this distribution does not have a constant rank, right? It's rank 2 for all x positive, because I will have h non-zero value here, right? But if x is negative, this guy will have just one vector. So this is not constant rank, which I mean is not regular, right? Okay? Okay, let's compute our two objects. What are two objects? The Lie infinity versus this guy, the tangent space, from the origin of f or delta. Okay? Let's compute these two guys. The Lie brackets are easy. Let's do that. So Lie infinity of delta. Let's get the first one. So no Lie brackets. No Lie brackets, so the span of the two vectors. Just the span of the two vectors, but evaluated at the origin. H of 0 is 0, so there is nothing. So it's just 1 and 0, right? It's just one-dimensional vector. That's okay. I'll keep adding velocity vectors by doing Lie brackets. So I'm doing x and y. So this is partial y, partial x, partial q's, minus partial x, partial q's, times y, and so and so. So this gives you what? What's y? Y is 0h. So this is 0, 0, h prime, and 0 times x, which is 1 and 0, minus x is constant, so this goes away. So you'll have 0 and h prime, but I'm sorry, I'm evaluating at the origin. So this is at the origin, so this guy is 0. So you'll have the 0 vector again. And keep doing it. So actually Lie1 of delta is the span of this guy and whatever we got with first order Lie brackets, we got nothing. So keep doing it, x and y, at the origin is also 0 because all the derivatives of h vanish at the origin. X and y at the origin is also 0 and so on. So you can write now Lie2 is just the same vector and yada yada. So the Lie infinity of this distribution or family of vector fields is just, I'm sorry, we couldn't add any more vectors by Lie brackets. It is just your actuator. X dot was u, my controller, and there was some natural flow here, which I'll give the name drift next time. So this did not provide anything. It's just your actuator that moves you in the x-axis. Any question about that? Let's see over there how we get the tangent space. Well, this theorem gives you a characterization of the tangent space in terms of these adjoint operators, in terms of these, the pullback. Actually, this is the example that we did at the beginning of the lecture. If you remember, psi was, so psi 1 may be the flow along x. So I have two vector fields, x and y, right? So psi 1 is flow along x, just flow along x. And I have psi 2 is flow along y, right? And so on and so on. I have many more psi's with by concatenations, compositions. So let's do psi 1 star times y. This is one of the vectors in the tangent space. We did that already up. It was 0 h of x plus t. Let's see it. Where is that? Long way. Here it is. The phi t x star pullback y. This is 0 h x plus t. Okay. So let's go back here. And again, like I told you, please substitute at the origin. So this is just one of the vectors there. Okay, so let's substitute at the origin. So x is 0. So this is h of t for some t. It depends on your time, but whatever. And we have this for all times, right? In particular, I have some t positive enough. So if t is positive enough, this will give you a positive value, right? T positive implies h of t positive. So this vector will give you motion along the y direction. So now the tangent space from the origin is the span of the vector field, this guy, right? Because I can have flow for 0 time, that's okay. The vector field y